Okay, I want to start this video off by explaining how we represent hydrocarbons. So up here I have 5 common ways that you'll see hydrocarbons represented by chemists. So the first way is simply their name, their English name. So for example, I have butane here, and butane is going to have a molecular formula which essentially tells you how many of each atom are in the compound. It doesn't tell you its shape, it doesn't tell you where the atoms are, but it tells you we have 4 carbons and 10 hydrogens in butane. You also will see this skeleton structure form of hydrocarbons. And what this basically means is that each corner or point is a carbon, and to the carbons are attached hydrogens. So you can see here that this point would be this carbon, and it has 3 hydrogens attached to it, and then it's attached to this carbon. So you can see this line here is a carbon-carbon bond, and then this carbon can bond with 2 other hydrogens because its other 2 bonding areas were taken up by these 2 carbons. And then this next corner here is this carbon, and it can bond with 2 hydrogens. And then the final point here is this carbon, and it has room to bond with 3 other hydrogens. So you can see how the skeleton structure is sort of like a shorthand for the structural formula. And then also you'll sometimes see what's called a condensed molecular formula, which is similar to the molecular formula, but it sort of shows you a little bit more of how the atoms are actually arranged. So you see here on the left we have CH3, carbon attached to 3 hydrogens, then CH2, CH2, so 2 CH2s, and then finally a CH3 at the end here. So it's a little bit informative than the molecular formula in terms of the structure. Another example here, propene. So the molecular formula, C3H6. The skeleton structure, you can see this has a double bond here, and that's how we'll represent that. And you can see that each point here is a carbon. So 3 carbons, 1, 2, 3. Each line is a carbon-carbon bond. And then we fill in the carbons with hydrogens because these are hydrocarbons. So this point here is a carbon with 2 hydrogens. This carbon here only has room for 1 hydrogen because it has 1, 2, 3 of its other bonds taken up by carbon-carbon bonds. And remember, carbon can make 4 bonds total. And then finally, this carbon here at this point has 3 hydrogens attached to it, and that's what that represents there. And then you can see the condensed molecular formula of propene looks like this. So CH2, that's this right here, CH in the middle, and then finally CH3 on the end. So the 3 main divisions of hydrocarbons in the aliphatic division are alkanes, alkenes, and alkynes. So aliphatic is kind of another word for a non-polar hydrophobic hydrocarbon. And that's not terribly important right now, but just know that these types of molecules are nonpolar and they don't like to be in water. So alkanes, these are a type of aliphatic hydrocarbons, and they have the general molecular formula CnH2n plus 2. So that means if we have N carbons, we have 2N plus 2 hydrogens. So in general, this is going to hold true. So let's say we had 8 carbons. So C8, and then H would be 2 times 8 plus 2, which would be 18. So if we had C8, we would need H18. Alkanes have all single bonds, and we say that they are quote-unquote saturated. So this is an example of an alkane, a hydrocarbon with all single bonds. And then alkenes, they're similar. They're made up of all hydrogen and carbon, just like all these hydrocarbons are. But there is at least 1 double bond in an alkene, so we say that it is unsaturated. So let me explain what I mean by saturated and unsaturated. When I say saturated, I mean saturated with hydrogens. I mean the carbons are saturated with hydrogen. So if we had an alkane here, I'm just going to draw, for example, this is actually ethane. It's an alkane. So notice here that the carbons are saturated with as many possible hydrogens as they possibly can be. So that is why this is an alkane that is saturated. But imagine I take away these hydrogens, and in place of them I make a double bond between the carbons. This is now ethene. It was ethane, now it's ethene, so it's an alkene now. Now the carbons are not saturated with as many hydrogens as they possibly could be, because we could have had 2 more hydrogens up here. So this is unsaturated. And this is the basis for, saturated and unsaturated fats that you see in foods. It's just the difference of having a double bond. Finally, alkynes, again, these are made up of all C's and H's, and the general formula is CnH2n-2. So for example, let's say we had C10, so N is 10, that means the H's would be 2 times 10, or 20 minus 2, so it would be C10H18 if we had 10 carbons. And in alkynes, there is at least 1 triple bond, and again, they are unsaturated because the carbons are not bonded with as many hydrogens as they could be. And the other main division of hydrocarbons are aromatic hydrocarbons. And these aren't quite as important in general chemistry, but what you should know is that the most common form of an aromatic hydrocarbon is a benzene ring. And aromatic is kind of a word for ring, and you can see here that we just have a ring of carbons and hydrogens. And this is the skeleton structure of benzene, and this is the structural formula. Okay, now I want to go into how we actually go about naming hydrocarbons. So you see we break it up into 3 parts here. The prefix denotes any substituents we have, and I'll explain that later. The parent denotes the length of the longest carbon chain or ring, the longest continuous carbon chain. And then the suffix denotes whether we have an alkane, or a hydrocarbon that's all single bonds, an alkene, a hydrocarbon with at least 1 double bond, or an alkyne, a hydrocarbon with at least 1 triple bond. So I've written up here some very bare basics rules for naming alkanes, alkenes, and alkynes. And I also have a chart up here that you really need to make sure you have memorized. So this tells you, based on the number of carbon atoms in a chain, what the name of that chain is going to be. And this is important for the parent part of naming the hydrocarbon. So I've got some very simple molecules up here, some very simple hydrocarbons that I want to name to start out, to make sure we're all on the same page with the bare basics. So the first one here, the first step is we label our carbons in our longest chain. So here we only have 1 chain, 1, 2, 3. And you can see here that there are no substituents. Substituents are things that are hanging off of the longest chain. And we don't have any of those in this case. So you can see here for naming alkanes, which is what this is, a hydrocarbon with all single bonds, there are no double bonds or triple bonds. We found the longest carbon chain, there's only 1, and we numbered the chain, and we didn't even have to worry about the side closest to the substituent or naming the substituents alphabetically, because we don't have any of those. We'll get to examples like that. So we see we have 3 carbons here in our chain, so that means this is prop, that's the parent. Remember, we didn't need the prefix because this is for substituents, so prop, and then it's an alkane, so propane. So this is propane. Okay, moving on to the second one. So here we have a double bond. So that means this is an alkene. So in alkenes and alkynes, you always number the chain from the end closest to the double or triple bond. So here we see the double bond is on this end. So that means this is carbon 1, carbon 2, carbon 3, and then carbon 4. It would have been incorrect to name it the other way around. We couldn't have said 1, 2, 3, 4. We have to name it starting with the end closest to the double or triple bond. So we know that this is a 4-carbon chain, so we see here that it is going to be bute, and also note we have no substituent, so no prefix, so bute is going to be our parent, and then the suffix is going to be ene, since it's an alkene. So this is going to be butene. And you'll see that actually with alkenes and alkynes, we have to denote where this double bond was. So this double bond started on carbon 1, right? So that means we have to denote it was 1 butene. We know from butene it was a 4-carbon chain with 1 double bond, and this says it started at carbon 1. Okay, the last example here. So we have a triple bond, so this is an alkyne. So the first step is we number the chain from the end closest to the double or triple bond. So we could name this 1, 2, 3, 4, or 1, 2, 3, 4. Either way, we both end up with the same proximity to this triple bond. It's always going to be the second carbon from this way or from this way. So it really doesn't matter. It's a symmetrical molecule. So I'll just pick this way. 1, 2, 3, 4 carbons. And again, it's an alkyne. And we don't have any substituents. These are all quite simple hydrocarbons. There's nothing hanging off of this chain here. Just as an example, you know, if I had like another carbon up here, that would be a substituent, and we'll get to those. So this last molecule, we have 4 carbon atoms in the chain, so it is going to be bute, and again, no substituents, so no prefix. So bute is the parent, and then it's going to be butyne, because it's an alkyne. But remember, like the last one, we have to denote where that triple bond is, because this tells us it's a 4 carbon chain with 1 triple bond. But where is the triple bond? Well, it's on carbon 2, so 2-butyne. Okay, going into some more examples here, so I want to name this molecule to begin with. So we notice they're all single bonds in this hydrocarbon, so this is an alkane. And we know that the first step in an alkane is to find the longest carbon chain. So the longest carbon chain, we can either start counting from here, here, or here. So let's see which one is the longest. So starting here, 1, 2, 3, 4, 5, 6, 7, 8. Okay, what about here? 1, 2, 3, 4, 5, 6, 7. And we could also have gone this way, 1, 2, 3, 4, 5, 6. So far this is winning. What about the other way? It's going to still be 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 4, 5, 6, 7. So certainly this long bottom chain is the longest with 8, any direction we go. But we want to number the chain from the side closest to the substituent. So if we're saying this bottom chain here, this chain of 8 carbons is our longest parent chain, then this thing up here is going to be our substituent. And it's actually going to be an ethyl substituent. I have a list of substituent names down here, and you can see that this little curved thing here means the rest of the molecule, and when you have 1, 2 carbons hanging off of your parent chain, we call that an ethyl group. So I'll go ahead and start numbering my carbons in my parent chain, which is the longest chain, from the side closest to the substituent, which was this here. And then I have to name the substituents alphabetically. So we only have 1 substituent, so we don't really have to worry about putting anything in alphabetical order. So remember, the general formula is we start with a prefix, and that's for our substituents. So we need to denote where this substituent is. It's on carbon 4. So we'll say 4, and we'll make a dash ethyl. And then we need to name our parent carbon chain, which it has 8 carbons, so that's going to be oct. And then the suffix, we know it's an alkane, so this will be 4-ethyl octane. Okay, so let's move on to this one here. So we see that we have at least 1 double bond in this hydrocarbon, so that means it is an alkene. And the rule for alkenes is we want to number the chain from the end closest to the double or triple bond. So here we see this is where the double bond starts, right? And we know that this carbon chain is going to be 1, 2, 3, 4, 5, 6 carbons long. And we want to start naming, numbering from the end closest to the double bond. So we'll start numbering from that end. 5, 6. So when you have 2 double bonds, you actually have to do something interesting. So we don't have any substituents, so we won't have a prefix. We know the parent is going to be 6 carbons, so hex. So you would think hexene, and we have to also denote where these double bonds are. This one starts at 1, and this one starts at 3. So you might think 1, 3 hexene, but when there are 2 double bonds, you actually say 1, 3 hexadiene for 2 double bonds. The di means 2, so this is 1, 3 hexadiene. Okay, moving on to this molecule here. So we see that there's at least one double bond, so again we have an alkene, and we want to start numbering the chain from the end closest to the double/triple bond. So this is a double bond, so we'll start numbering here, 2, 3, and clearly the longest parent chain is going to be if we continue on here, and these two methyl groups are going to be substituents off of carbon 3. So we have a 7-carbon chain. That's our parent chain. And again, we do have substituents in this case. That's going to be our prefix. So we'll start by naming these substituents. So these are both methyl groups on carbon 3. So to denote where they are, we'll say 3, 3 dimethyl, because there are 2 methyls. So that's how we name the substituents. Then we have to name our parent chain, and we know it's 7 carbons long, so it will be hept. But how do we account for including that this double bond is on the first carbon? Well, we can say, similar to how we've done before, that this is 1 heptene. So that tells us that the double bond that makes this an ene is on carbon 1 out of 7 total. So you can see here that this naming system was devised so that you could look at the name without having this blue skeleton structure and be able to draw this. So now from this we would know that on carbon 3, there are 2 methyl groups, and then it's a 7-carbon parent chain, and it's got a double bond somewhere because it's an ene, and that starts on carbon 1. So it gives us all the information we need. Okay, moving on to this last structure here. So we see it has at least one triple bond, so that means it's an alkyne. And we want to start numbering the chain from the end closest to the double or triple bond, which is going to be this end here, right? Because if we go 1, 2, it'll be on carbon 2, versus if we went on this end, 1, 2, 3, 4. So we'll start numbering from this end. 1, 2, 3, 4, 5, 6. So you can see this is a 6-carbon chain, and we don't have any substituents, right? We don't have anything hanging off of any of our parent chain carbons. So we'll start with the parent chain. There's 6 carbons, so it's a hex, and then we know the suffix is going to be "-ine" because it's an alkyne. But what do we have to do here so that someone knows how to draw this blue structure from our name? Well, if we just say hexyne, they don't know where to put the triple bond, right? So we have to say that this is 2-hexyne. So I hope that makes sense. Okay, a couple more examples here. So you can see we've got 2 fairly complicated looking hydrocarbons, and they're both made up completely of single bonds. So these are both examples of alkanes. So if we want to name these, the first step is to find the longest carbon chain, and we want to number the chain from the side closest to the substituents. So we can see here that it looks like we may even have 2 substituents on this chain. So that'll be a good example of how we have to order them alphabetically. So if we want to find the longest carbon chain here, well, it looks like it's probably going to be this one down the middle. So 1, 2, 3, 4, 5, 6, 7, 8. And you could test the other ones, you know, you could count from here or here or here, but you're not going to be able to find one as long as that one. That's the longest chain. And we want to number them from the side closest to the substituent. So the substituent appears to be closer to this side. So I'll name the carbons 1, 2, 3, 4, 5, 6, 7, 8. So I have an 8-carbon long parent chain, and it looks like I've got 2 substituents here, one coming off of carbon 4 and one coming off of carbon 5. So the one coming off of carbon 4 kind of looks like a cross, right? So what sort of substituent is that? I've got a list of them down here. So this is actually an example of tert-butyl. Okay, it's kind of a weird name, but if you see here, it's something sticking off of the rest of the molecule that splits off into one carbon with 3 of them coming off of it, and that's the situation we have here. Here's the carbon and then the 3 branching off of it. That is a tert-butyl group. Okay, and then what about carbon 5? It's got, well, just a simple ethyl group coming off of it, right? So we need to denote, first of all, that this is an 8-carbon chain with the parent chain, but also that it's going to have a prefix. We have 2 substituents in this case. So we name them alphabetically. But the trick here is that if you have a prefix like iso, sec, or tert, you don't use those prefixes when you consider the alphabet. So let me explain what I mean by that. So I have 2 substituents here, tert, butyl, and ethyl. I don't consider this prefix in my alphabetical ordering, so I will determine which one comes first by these letters. So butyl comes first in the alphabet, so that means I'll name that substituent first. So that means this is going to be 4 tert butyl. The tert is still in the name, we just don't use it to determine alphabetical ordering. And then 5 ethyl. And I'm sorry, there should be another dash in front of that 5. And then what is the parent chain? There's 8 carbons, so it's oct, and we know it's an alkane, so this is going to be octane. So that is the full name here. And if you notice, if you only had this name, if you're good at, drawing these hydrocarbons, you should have all the information you need to draw this. We know that it's an 8-carbon parent chain, and it's an alkane, so they're all single bonds. And then at carbon 4, we would have a tert butyl group, and then at carbon 5, we would have an ethyl group coming off of it. Those are the substituents, okay? So what about this next one here? Well, that's kind of a cool looking molecule, isn't it? But we know that it's an alkane, and that's because they're all single bonds. So let's try to find the longest carbon chain and number from the side closest to a substituent. So what is the longest carbon chain you guys can see here? Well, we could try counting from here. 1, 2, 3, 4, 5. Or this one looks pretty long. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So they're all really 5. So I'm just going to pick the one that looks the most familiar to me. 1, 2, 3, 4, 5. And it doesn't really matter which side I start on, right? I could have started over here because these methyl substituent groups are both 1 carbon away from the end. So we could have gone either way. So notice here we have actually 3 substituents this time. A methyl group here, and then what is this group down here? Kind of looks like a Y-shaped. And you can see that's isopropyl. So we have a methyl group here, an isopropyl group here, and another methyl group here. So we want to name them in alphabetical order. So we have 2 methyls, so that is going to be dimethyl. And then we have isopropyl, so isopropyl. But remember, we don't consider these prefixes when we do our alphabetical ordering. So we will only consider the M and the P to see which one is going to come first alphabetically. So M comes before P, so we will do 2,4-dimethyl, so 2,4-dimethyl. Remember, this is our prefix that we're doing for the substituents. And then isopropyl comes off carbon 3, so 3-isopropyl. And then how many carbons are in our parent chain? 1, 2, 3, 4, 5. So this is going to be pentane for alkane. So where there's no dash in between here, we just end with pentane. So that is how you name those 2 molecules. All right, I want to finish this video off by discussing isomers. So isomers are actually quite interesting. It's the concept that you can have molecules that have the same molecular formula, and in some cases even the same atom-to-atom attachments, but they're actually different molecules with different properties. So how is that possible? Well, there are 2 main divisions of isomers. There are structural and stereoisomers. Structural isomers are 2 things that have the same exact molecular formula, for example C4H10, but they have different atom-to-atom attachments. So both of these molecules have 4 carbons, 1, 2, 3, 4, 1, 2, 3, 4, but you can see they're connected in different ways. So they're structurally different, although they have the same molecular formula. So this is butane and then isobutane. The other main class of isomers is stereoisomers, and these are even more interesting because the atoms actually have the same connections, they're just oriented differently in space. So there are 2 types of stereoisomers, geometric and optical. And for this class, what you need to know is that geometric isomers have different attachments of atoms on either side of a double bond. So all the atoms are still connected to the same other atoms, it's just they're on different sides of a double bond. And we know that a double bond can't be rotated because of some orbital principles. So this is actually cis 1,2 dichloroethene, because the chlorines are the substituents and they are on the same side, so we call that cis, and they're on carbons 1 and 2, and we know that this is ethene because there's a double bond. On the other hand, notice how in this case the carbons are still attached to an H and a Cl, just as they were before, HCl, HCl. But in this case, the chlorines are trapped on opposite sides of the double bond. And we know this double bond can't be rotated around, so they're going to be stuck there. So we call that trans because they're on opposite sides of the double bond. Trans 1,2 dichloro because there are 2 chlorine substituents, ethene. So those are geometric isomers. So optical isomers. This is where you have a carbon attached to 4 different atoms and it creates something called a chiral center, and this forms optical isomers, pairs of optical isomers. So here you see we have a carbon attached to 4 different things. So here it's attached to a methyl group, a bromine, a chlorine, and a hydroxide group. There are 4 different things coming off of that carbon. And because of that, they form a chiral center around the carbon. On both of these carbons there's a chiral center, and these are what's known as optical isomers. So this is the idea of kind of a left and right hand. So look at your hands. You know, they're the same shape, they have the same fingers coming off of both of them, but when you put them on top of each other, they're not the same in 3-dimensional space, right? They don't fit over one another. They're optical isomers. So this confused chemists for a long time. You can have 2 molecules that seemingly have the same shape, the same attachments in 3-dimensional space, but when you superimpose them, they don't quite match. So those are the 3 main types of isomers that you'll be responsible for. I really hope this helped you guys out. If you have any questions, please let me know on facebook.com/denovotutoring. See you guys in the next video.